Right. So, welcome to the PowerPoint associated with atoms, isotopes, and ions. Uh, while you work your way through this, I would encourage you to write down highlight items, since a number of these items are definitions as well as examples of things that'll be talked about. What I don't recommend you do is to blindly just copy everything down from a slide, but rather try to put it into your own words. Um, the ideas behind atoms really go back uh, several centuries, and its development culminated in the work ultimately of John Dalton, who is considered the father of chemistry. Um, John Dalton put together what is now known as the atomic theory. And the atomic theory um, did not uh, describe details of the atom structure. Rather, it recognized that and really put to rest the idea that matter is made up of atoms. And I recognize that you can read all the items on the chart, but I'd like to briefly kind of elaborate on the ideas given. So let's take a look at them now. Um, Elements, which is a general term used for matter, which is made up of the same kind of atom. For example, a silver coin is a element or collection of silver atoms. And what happens is all matter is made up of these small particles, which we call atoms. The details of which you will have been worked with in class. Um, One needs to recognize that the atoms of a certain kind of element are absolutely identical in the mass or weight, and more importantly, the atoms chemically have the same behavior when they're from a pure element. For example, silver may have a certain color to it, and all silver atoms have that color, whereas copper atoms, because it's a different atom, has a different color to it. The weight of a copper atom is different from the weight of a silver atom, a different mass, if you will. Um, Atoms are able to combine with each other. Um, and for example, you can have um, two hydrogen atoms are able to combine with one oxygen atom to make H2O or water. Now notice what you cannot have. You cannot have two and a half hydrogens and one oxygen. A half atom is not possible. And so atoms, when they do combine to make a molecule or a compound, always combine in whole ratios. In the case of water, it's 2 to 1, H2O. In the case of methane, it's CH4 with 4 hydrogens and 1 carbon. So you cannot have partial atoms. When molecules chemically react, they recombine. So when I take methane, CH4, and I combine it with oxygen gas, which is O2, we can create a new combination of water and carbon dioxide. But realize that the carbon that makes up methane, CH4, is in fact the same exact atom that makes up the carbon of carbon dioxide, CO2, which is a product. So when we do chemical reactions, we're not changing the atom itself, we're simply rearranging or recombining it. Now, every element, every atom has certain items or properties that we need to, as chemists, be able to write down in a shorthand manner. And so what typically happens is a small rectangular box is written, and into that box very specific items are noted about that atom. First of all, every atom is given a symbol. Fe is the symbol for iron. And the reason why Fe is used goes back all the way to the alchemists, which is a few centuries ago. And they used Latin to name the elements. And the Latin word for iron was ferrous, and so Fe is used as the symbol. And a number of symbols are match the English. For example, C represents carbon, but you will find some unusual symbols which don't match up, and that goes back to the alchemists. So we have the atomic number. The atomic number is given the letter Z. And the atomic number tells you how many protons there are. And as we'll find out shortly, the number of protons is what determines the kind of atom that you have. So all iron atoms have 26 protons. The atomic number for all iron atoms is 26. If you have 12 protons in there, you no longer have iron. What you have is carbon. Because the number of protons is what determines the kind of atom that you have. You will not be asked to memorize how many protons or the atomic number for each element. You do need to know, though, that it does appear usually at the top of the box in this case. The atomic mass is the average atomic mass, and that's on the bottom. In this case, it's 55.85. The atomic mass is an average because although all iron have the same number of protons, 26, it does not always have the same number of neutrons. There's a different number possible in there. Some iron atoms have 27 neutrons. Some iron atoms have 24 neutrons. And the number of neutrons can vary. Those are called isotopes. But it makes for a different weight among different iron atoms. And so what chemists have done is they average the number of they average the weight of the different kinds of iron atoms and give you an average atomic mass. Be aware that the element or that atom called iron cannot be divided, it cannot be reduced in size, it cannot be modified. It is the rock bottom, that's it, that's as far as you can go in dividing iron up. The atom itself, whether it's a hydrogen or a helium or an iron atom or uranium, all atoms have the same basic structure. And that structure is a layout that you see in front of you. It is made up, the atom itself, that's one atom we're looking at, is made up of several smaller components. Those smaller components are called subatomic particles. Inside, in the middle, you have the nucleus, and the nucleus itself is made up of two types of particles. One is called a neutron and one is called a proton. And the proton has a property to it in that it has an electrical charge, and that charge is a plus. It also doesn't weigh very much, as you can tell. The neutron is also in the nucleus, or makes up the nucleus, and it also weighs very, very little, but it has no charge. You will notice that the neutron is ever so slightly heavier than the proton, and that is because the neutron is actually a combination of a proton plus an electron together, and that's why the charge is neutral. From a chemist standpoint, it's so close that we consider the weight of a proton and the weight of the neutron to basically be the same, although it is ever so slightly different. Now, when you look at an electron going around the outside in the shells, which was first proposed by Niels Bohr, the electron has an interesting idea. It has an electrical charge. It's negative. In fact, the amount of charge it has is the same amount of charge as a proton, but it's negatively rather than positively charged. But what's unusual is the electron weighs a lot less. It's almost 2,000 times less massive than the proton. But the amount of charge that the electron has in itself is in fact the same amount. So the charge is not dependent on how much it weighs. Now let's break down this a little bit better. The atomic number, which is given the letter Z, is the number of protons in the nucleus. It also is the number of electrons, but only in a neutral atom. And that's because the number of electrons and the number of protons counteract each other's charges and produce a neutral charge. Crucial is that the number of protons is what determines the kind of atom you have. Carbon, for example, has 12 protons, and carbon is carbon because of the 12 protons. You can actually change the number of electrons. You can give more electrons or less electrons to carbon, but it's still carbon because the proton is what determines it. Now you have what is referred to as isotopes. And the isotope is the same kind of atom, except for the number of neutrons can vary. So what we see here is in this atom, the number of protons is 1. And because it has 1, this overall atom is considered hydrogen. You'll notice the same number of protons is here and here. So all of these 3 atoms are all considered hydrogen. But there is a slight difference. This particular atom here has a neutron in it. And this one here has 2 neutrons in it. Now, obviously, this atom of hydrogen and this one, they don't weigh the same because I have more particles in the nucleus here and even more here. However, the neutrons do not change the chemical properties of hydrogen. Now, what does that mean? Well, it means that if this hydrogen right here was being used to make water, it would be one of the hydrogens. This atom of hydrogen can do the same thing. It can be part of water, H2O. This one could be used as an atom of hydrogen to make H2O. So the chemical properties of all 3 of these types of hydrogen are the same, although they have a different number of neutrons. And because they have a different number of neutrons, we call these isotopes. So these are all hydrogen atoms, but they are different isotopes of hydrogen because of the difference in the number of neutrons. So we can represent all this information in a certain format. You'll notice we're not drawing a rectangular box around this like we had originally, but rather we're going to list all the chemical properties, all of the physical properties that show up here. Here you would write the chemical symbol. For example, you could write H, or you could write Fe. And then in the upper left portion of that symbol, you would write the mass number. Now, the mass number, as it indicates here, is the physical number of protons plus the physical number of neutrons. It's the sum of those two, and you place it there. You'll notice in the lower left here, you write the atomic number. Remember, the atomic number is the number of protons. So, if you were to write out the symbol, full symbol, for this particular hydrogen, you'll notice the total number of particles in the nucleus is 1. The total number of protons is 1. And it's given the name hydrogen 1 because the total number of particles, which would be protons plus neutrons, that total is 1, so you'd call this hydrogen 1. In this case, it's still hydrogen because there's only one proton. Remember, it's the proton that gives you the type of atom you've got, but there are 2 items in there. 1 proton, 1 neutron, and so we now are going to change the mass number to 2. The number of protons hasn't changed, so the atomic number is still 1. You would call this hydrogen 2 because it has the 2 particles. And of course down here it's going to be hydrogen 3 because you have 3 total particles in the nucleus, but again only one of them is a proton. So let's expand now this layout. What we have is, this is the nucleus. We have the electron cloud on the outside. This is a atom that has 25 protons in the nucleus, which is plus, and this one has 30 neutrons. The charge on that is 0. And because the mass of an electron is so small, remember it's 2,000 times less than the mass of a single proton, we ignore whatever number of protons there are in terms of the mass, and we would simply list it that way. You'll notice in this drawing we did not draw all 25 protons and all 30 neutrons. Instead, we simply draw a dark, dense area and then identify how many protons and neutrons there are. Now, this particular atom we would call neutral. The atom's neutral because the number of electrons and the number of protons, that number matches up. And therefore, the charges cancel out, and the overall charge of the atom is 0. Now, let's take a look at this. This atom is sodium. It is sodium because there are 11 protons in it. This number is what told you it was sodium. This particular sodium atom has 12 neutrons in it. So if you add the 11 and the 12, the total number of subatomic particles in here is 23. So you write the symbol Na, that stands for sodium. Again, that's going back to the alchemists. You write up here the mass number, which is the total number of particles, which is 23. This is the atomic number down here, which is the number of protons. And you would call this sodium 23 because there are 23 total particles. Now, silver the symbol for silver is Ag. Silver is silver because there's 47 protons. You can see that listed here. But the total number of particles in the nucleus is 62. Therefore, if you add up the number of neutrons, 62, and you add up the number of protons, 47, that gives you the mass number, which is right here, and you'd have silver as 109. Now, what you need to notice is that this is sodium. It's a type of metal, actually. It's easy to carve with a knife. It's very soft. This is raw silver. It doesn't particularly look silvery, but that's because this is how it comes out of the earth, and that purify it. Now you'll notice that this and this substance, this and this type of matter, they're different chemically. Why are they different chemically? Ultimately, because there are 47 protons in silver, the overall property of the silver atom gives you this material, which is made up of billions and billions of the silver atom. The sodium atom is made up of 11 protons, and because of that, the sodium atom has certain properties. If you put a whole bunch of sodium atoms together, it has this overall property here. Now, what about the element symbols? Well, as I say, the element symbols is the shorthand abbreviation for the name itself. And there are certain rules to how you do that. What you do is the first letter, if there are two letters, the first letter is always capitalized and the second letter is lowercase. So this is cobalt. You would not write it this way. If you do write it this way, people interpret this as a molecule now, which is an atom of carbon and an atom of oxygen. Well, we don't want to do that. We want to talk about just cobalt, and so you follow the rule here. You can see that again over here. The manganese is a capital N and lowercase n, and you don't do it here like this because that's not going to be manganese. So when you look at the periodic table, you have either one letter, in this case carbon. You can use two letters such as cobalt, which is a capital letter and lowercase, and on rare occasion you can actually have three letters. Usually the three letters correspond to a man-made or non-natural element. So what we've seen is atoms are the basic unit of matter, and if I get a collection of atoms together of the same type, for example, a collection of silver atoms, a collection of cobalt atoms, we call that an element. An element is simply a collection of the same kind of atom. Now, atoms do connect to each other. And when they do, they sometimes connect to the same kind. So, for example, hydrogen can connect to itself. And this is how you would write two hydrogen atoms connected to each other. You list the element H, and then you have a lowercase 2. And now this is no longer an atom, but rather this becomes a molecule. And this particular molecule consists of two atoms connected to each other. They're the same kind of atom, so we call them diatomic. So this is a diatomic hydrogen, diatomic nitrogen, oxygen, etc. These are the only 7 atoms that can connect to themselves. So you cannot have two cobalt atoms connect together to each other. You cannot have two carbon atoms connect to each other and that's all, just the two carbons. So only hydrogen, nitrogen, oxygen, they can connect to each other and be all stand alone. No other connections are needed. So those are your diatomic, and you have to memorize these. You're expected to know that. Sometimes atoms, several of them can connect together. For example, phosphorus. 4 phosphorus can connect to each other. 4 arsenic atoms can connect. 8 sulfur atoms can connect. You don't need to memorize this set, but you do need to memorize these here. Now, I'm not going to go into detail just yet about the periodic table, but I did want to show something that many of you are familiar with, which is that the atoms are arranged here, and that the symbols, the atomic weight, the average atomic mass, and the name is given to them. And this here reminds you what those different areas are. You have this in your lab manual, and you'll be using it very, very extensively.